Your AI agents weren't designed for connectivity, they were designed for reasoning, models, prompts, token windows. And the assumption that the data would somehow find its way to them, that assumption is broken. Because agentic work doesn't start with reasoning, it starts with the connection. And the protocol that builds that connection is already inside Microsoft Copilot Studio, Azure, and Dynamics 365. This is the architect's guide to MCP. The connectivity crisis. Every organization is running AI pilots now, Copilot is licensed, agents are deployed, and the demos look great in the boardroom. But in reality, something is missing. The model can reason, it can draft emails, it can summarize meetings, it can write code. But when you ask it to check inventory against your ERP or route an approval through your custom workflow or pull context from 3 different systems at once, it hits a wall. Not because the model isn't smart enough, but because the connection doesn't exist. And here's where most architects miss the structural problem. The issue isn't that Microsoft lacks APIs. Microsoft Graph is extensive, Power Platform has connectors for hundreds of systems. Azure has every integration pattern you could want. The problem is that none of these were built for agents. They were built for humans. A human opens SharePoint, navigates to a folder, finds a document and reads it. An API call retrieves the same document. But an agent doesn't browse. It doesn't navigate. It reasons. It needs to discover what it can do, understand the parameters, invoke a capability, and receive a structured response it can use in its next reasoning step. Traditional APIs don't provide that contract. Custom connectors in Power Platform come close, but they break on schema changes. They require manual configuration for every environment. And they were designed for Power Apps and Power Automate, not for large language models that need to discover capabilities dynamically. Direct API calls are even worse. Every integration is bespoke. Every auth mechanism is different. Every payload format is custom. And when your API version changes, your agent breaks silently because there's no capability negotiation, no handshake, no standard contract. So what's actually happening in most organizations is this. The AI team builds a beautiful agent that can reason about customer data. Then they spend 6 months writing brittle wrapper code to connect it to the CRM. Then the CRM upgrades. The wrapper breaks. The agent starts hallucinating because it's receiving responses it no longer understands. This isn't a model problem, it's an integration architecture problem. And it's costing organizations more than they realize. Every brittle integration is technical debt that compounds. Every schema change requires rework. Every new data source requires another custom wrapper. And the agents themselves are reasoning on stale context because nobody built the bridge to keep their knowledge current. The organizations that are winning with AI right now aren't the ones with the best models. They're the ones with the best connectivity layer, the ones that figured out that an agent is only as good as the systems it can reach. And until now, there was no standard way to build that layer in a Microsoft environment. That's where MCP changes the structural assumption. What is MCP? The protocol that changes everything. MCP stands for Model Context Protocol. It was originally developed by Anthropic as an open standard for connecting AI assistants to data sources, tools, and external systems. But what started as one company's experiment has become the connectivity backbone that the entire industry is converging on. And Microsoft isn't just adopting it, Microsoft is baking it into every layer of their stack. So what is MCP structurally? At its core, MCP is a JSON-RPC 2.0 protocol. That means it uses a standard remote procedure call format where a client sends a structured request and a server returns a structured response. But MCP adds something critical on top of that foundation. It adds discovery. An MCP server doesn't just expose endpoints, it exposes capabilities. When an MCP client connects to a server, they perform an initialization handshake. The server announces what tools it offers, what resources it can provide, and what prompts it supports. The client announces what it can handle in return, and only after this negotiation do they start working together. This changes everything. In a traditional API integration, the client needs to know the API surface in advance. You write code against a Swagger document. You handle version changes manually. You hardcode endpoint paths. With MCP, the client discovers the surface dynamically. The agent asks the server, "What can you do?" The server replies with a typed catalog. The agent then selects a tool, provides the parameters, and receives a structured response. This means your agent can adapt to new capabilities without code changes. When you add a new tool to your MCP server, every connected agent sees it immediately after reconnection. There's no deployment cycle on the client side, no version pinning, no breaking changes. MCP defines 4 core primitives that make this possible. Tools are callable functions exposed by the server. Each tool has a name, a description, and a typed parameter schema. The agent reads the description, understands what the tool does, and decides whether to invoke it. This is how an agent triggers a workflow, queries a database, or updates a record. Resources are read-only data sources addressed by URI. Think of them as files, documents, or reference data that the agent can pull when it needs context. A resource might be a SharePoint document, a product catalog, or a policy manual. Prompts are templated instructions that the server can offer to the client. They're not prompts in the sense of a chat message. They're reusable patterns that help the agent structure its reasoning. A server might offer a prompt for summarizing financial data in a specific format, or for drafting compliance reports using company templates. Sampling is the inverse relationship. When the server needs the client to generate content, it can request a sample. This allows the server to use the AI model's reasoning capabilities without hosting its own model. It's a subtle but powerful pattern for distributed intelligence. Together, these four primitives create a complete contract between an agent and the systems it needs to interact with. But why JSON-RPC 2.0 specifically? The protocol architects had a choice. They could have built MCP on REST. REST is familiar. Every developer knows it, every framework supports it, and it works well for human-facing web applications. But REST isn't designed for machine-to-machine reasoning. A REST API exposes resources at URLs. A client performs get, post, put, and delete operations on those URLs. The client needs to know the URL structure in advance. It needs to understand the HTTP status codes, and it needs to pass the response body to extract meaning. JSON-RPC 2.0 is different. It's a message-based protocol. The client sends a message with a method name and parameters. The server executes the method and returns a result. There's no URL structure to learn, no HTTP verbs to map, no status code semantics to interpret. This matters for AI agents, because agents don't browse, they reason. An agent looking at a REST API needs to understand that get means read, post means create, and delete means remove. It needs to know that a 404 status means not found, and a 500 status means server error. It needs to construct URLs by concatenating path segments and query parameters. An agent looking at a JSON-RPC API needs to understand one thing: the method name. The method name tells the agent what capability is available. The parameter schema tells the agent what inputs are required. And the response schema tells the agent what outputs it will receive. This is a much simpler reasoning surface, and that's why MCP chose JSON-RPC 2.0, not because it's newer or better than REST in general, but because it's better for agents that need to discover capabilities dynamically and invoke them without understanding the underlying HTTP semantics. The protocol also supports batch requests. A client can send multiple JSON-RPC messages in a single payload. The server processes them and returns a batch of responses. This is efficient for agents that need to invoke multiple tools to answer a single user query. And here's why this matters in a Microsoft environment specifically. Your organization already has the data. It's in SharePoint, it's in OneDrive, it's in Teams conversations, it's in Dynamics 365, it's in SQL databases running on Azure, it's in custom line of business applications that your teams built over the last decade. What you don't have is a standardized way for AI agents to discover, access, and reason over all of that data without writing bespoke integration code for every source. MCP doesn't replace Microsoft Graph. It doesn't replace your REST APIs. It doesn't replace your custom connectors. It sits above them. MCP is the translation layer, the normalization layer, the protocol that turns your heterogeneous backend systems into a uniform surface that any agent can understand. An MCP server for SharePoint doesn't just wrap Graph API calls. It exposes tools like find documents related to this project with parameters the agent can reason about. It exposes resources like the current project charter addressed by URI. It exposes prompts like summarize this document using our executive summary format. The agent doesn't need to know how SharePoint works. It just needs to know what the MCP server can do. And one level deeper, this is where the real shift happens. Because once you have an MCP server, any agent can use it. Not just Copilot, not just your custom chatbot, any agent that speaks MCP. That means the investment you make in building an MCP server for your ERP pays off across every AI initiative in your organization. That's the structural change. That's why this isn't just another integration pattern. The Microsoft MCP ecosystem, a landscape overview. Microsoft didn't just add MCP support as an afterthought. They built it into the architecture. Let's walk through where MCP shows up across the Microsoft ecosystem right now, because the breadth is wider than most architects realize. Microsoft Copilot Studio added Model Context Protocol support and took it to general availability in March 2026. This isn't a preview feature anymore, it's production ready. And the GA release included tool listing capabilities, enhanced tracing for debugging, agent-to-server communication, and infrastructure for scalable deployments. What this means practically is that any agent you build in Copilot Studio can now connect to external MCP servers as natively as it connects to Microsoft Graph or Dataverse. The tools exposed by your MCP servers appear in the agent's tool catalog. The agent discovers them during initialization, and it invokes them through the same reasoning pipeline that handles built-in Microsoft tools. Microsoft also published a Model Context Protocol lab on GitHub in April 2025. This is a collection of templates, sample servers, and learning exercises specifically for Copilot Studio integration. If you're starting from zero, this is your fastest path to a working prototype. But Copilot Studio is just the start. Dynamics 365 Finance and Operations added MCP server support in April 2026. You can now build and connect MCP servers that extend the capabilities of your ERP agents. That means your inventory agent doesn't just query stock levels. It can trigger reorder workflows, check supplier lead times, and update purchase orders through a standardized protocol surface. Visual Studio is shipping Azure MCP tools inside both Visual Studio 2022 and Visual Studio 2026. Developers can connect their IDE to MCP servers for code context, documentation retrieval, and even build automation. The same protocol that connects your business agents is now connecting your development environment. And all of this is underpinned by the official CR SDK. Microsoft released version 1.0 of the official MCP CR SDK in March 2026. This isn't a community project. It's maintained on GitHub in collaboration with the core MCP team. It's available on NuGet as the Model Context Protocol package version 1.40 as of late March 2026. Version 1.0 supports the 2025-1125 MCP specification. It includes hosting extensions, dependency injection support, enhanced authorization flows, icon support for tools and resources, richer metadata, tool calling enhancements, and long-running request handling. The SDK was updated in July 2025 to support protocol version 2025-0618, which brought structured tool output, elicitation support, and enhanced security features. If you haven't looked at the SDK since early 2025, it's a completely different animal now. But here's where things get really interesting from an architect's perspective. The transport layer is evolving. MCP started with STDIO transport, standard input and output. And this is perfect for local development. Your MCP server runs as a local process. The agent talks to it through pipes. It's simple, fast, and requires no network configuration. Then MCP added server-sent events for remote connections. SSE allowed a server to push updates to a client over an HTTP connection. It worked. But it had problems with authentication, CORS policies, and enterprise firewall configurations. So the MCP specification deprecated SSE and replaced it with streamable HTTP. Streamable HTTP uses standard HTTP post and GET requests. It supports optional server-sent events for server-to-client streaming where needed. But the core communication is plain HTTP, and that means it works with standard load balancers, standard firewalls, and standard authentication mechanisms. For Microsoft environments, this is critical because streamable HTTP integrates with Microsoft Entra. It works behind Azure API Management. It scales on Azure functions. It doesn't require WebSocket support or custom proxy configurations. We'll dig into transports in detail soon. But the main point is this: Microsoft isn't just supporting MCP as a protocol. They're optimizing their entire cloud platform for MCP deployments. Then there's the governance layer. Microsoft Entra Agent ID launched in early 2026. It's an identity and security framework specifically for AI agents. It lets you build, discover, govern, and protect agent identities at enterprise scale. And in May 2026, Microsoft added conditional access for agents, extending zero trust principles to non-human identities. Microsoft Agent 365 is the control plane. Observe, govern, and secure AI agents using the same Microsoft 365 and Microsoft security controls you already have. And there's WorkIQ. WorkIQ is the intelligence layer that personalizes Microsoft 365 Copilot and your custom agents with real-time, shared context across your organization. It pulls from SharePoint, OneDrive, Teams, email, and meetings, and Microsoft open-sourced a WorkIQ MCP server on GitHub. Finally, there's the agent-to-agent protocol. Google launched A2A in April 2025. Microsoft announced support in May 2025. And in June 2025, Google donated A2A to the Linux Foundation, with founding members including AWS and Cisco. A2A isn't a competitor to MCP. It solves a different problem. MCP connects agents to tools. A2A connects agents to other agents. You need both. So the landscape looks like this. At the bottom, you have your data and systems: SharePoint, Dynamics, SQL databases, custom applications. Above that, MCP servers expose capabilities through a standardized protocol. WorkIQ adds organizational intelligence. Entra Agent ID and Agent 365 secure the connections. Copilot Studio and custom agents consume the capabilities. And A2A enables those agents to collaborate. This is the connectivity architecture Microsoft is building. And it's not a roadmap slide. It's shipping now. MCP architecture deep dive. Before you start building, you need to understand how MCP actually works under the hood, not the marketing description, the wire protocol. Because the architecture decisions you make here will determine whether your MCP deployment scales, whether it remains secure, and whether your agents can actually discover the capabilities they need. MCP runs on JSON-RPC 2.0. If you've worked with remote procedure calls before, this will feel familiar. If you haven't, the concept is straightforward. A client sends a request with a method name and parameters. A server processes the request and returns a response. If something goes wrong, the server returns an error object with a code and a message. But MCP adds a critical layer on top of raw JSON-RPC. It adds the initialization handshake. When an MCP client first connects to a server, they don't immediately start invoking tools. They negotiate. The client sends an initialized request with its protocol version, its supported capabilities, and its implementation details. The server responds with its protocol version, its capabilities, and its implementation details. Only after both sides agree on the contract do they transition to the ready state and begin normal operation. This handshake is why MCP servers and clients can evolve independently. A server running protocol version 2025-1125 can talk to a client that supports version 2025-0618. They negotiate the common subset. If the server offers a feature the client doesn't understand, the client simply ignores it. If the client requests a feature the server doesn't support, the server returns a clear error. This is capability negotiation in practice. And it's fundamentally different from REST API versioning. With REST, you typically version the entire API surface. V1, V2, V3. When V2 drops a field that V1 had, every client breaks unless it was already updated. With MCP, capabilities are granular. The server advertises what it has. The client selects what it needs. Changes are additive by default. Let's look at the 4 primitives in detail. Tools are the most commonly used primitive. A tool is a callable function exposed by the server. The server defines the tool's name, provides a description that explains what the tool does, and specifies a JSON schema for the parameters. This schema is typed. It tells the client exactly what inputs the tool expects, what types they are, and which parameters are required. When an agent wants to use a tool, it doesn't just guess the parameters. It reads the schema, it reasons about what values to provide, and it invokes the tool with a properly structured request. The server executes the tool and returns a result. Here's where the 2025-0618 protocol update changed things significantly. Before that update, tool results were typically simple strings. A tool might return a block of text, and the agent would parse that text to extract meaning. This was fragile. If the tool output format changed, the agent's parsing logic broke. The 2025-0618 update introduced structured tool output. Now tools can return typed objects, arrays, and nested data structures. The agent receives a structured result it can reason over directly. No parsing, no regex extraction, no brittle string manipulation. This matters for enterprise integrations because your business systems already return structured data. A query against your ERP returns records with typed fields. An inventory check returns quantities, locations, and status codes. With structured tool output, that data flows directly into the agent's reasoning pipeline in its native shape. Resources are the second primitive. Where tools are active operations, resources are passive data sources. A resource is addressed by a URI, just like a web page. The server defines what URIs it supports and what content they return. When an agent needs context, it can request a resource by URI. The server returns the content, typically as text that the agent can embed into its reasoning context. This is how an agent reads a policy document, pulls a project charter, or retrieves a customer record. Resources are read only by design. If an agent needs to modify data, it uses a tool. This separation creates a clean architectural boundary. Resources provide context. Tools perform actions. Prompts are the third primitive, and they're often misunderstood. An MCP prompt is not a user message. It's a template that the server offers to help the client structure its reasoning. A server might expose a prompt for generate a quarterly financial summary in the CFO's preferred format. The prompt includes the template structure, variable slots, and instructions for how to fill them. When an agent needs to perform a complex reasoning task, it can request a relevant prompt from the server. The server provides the template. The agent fills in the variables and uses the resulting structured instruction to guide its output. This is particularly valuable in Microsoft environments where organizations have standardized formats, compliance templates, and brand guidelines. The MCP server encodes these standards as prompts, and every connected agent automatically produces output that follows them. Sampling is the fourth primitive, and it's the inverse of the other three. Sampling allows the server to request generative reasoning from the client. When a server encounters a problem that requires AI reasoning, instead of hosting its own model, it asks the client to generate a response. This creates a distributed intelligence pattern. The server handles business logic, data access, and system integration. The client handles language understanding, summarization, and generative reasoning. They collaborate through a standardized contract. In a Microsoft environment, this pattern is powerful because your MCP servers don't need to host or manage language models. They use the reasoning capabilities of Copilot, Azure OpenAI, or whatever AI client is connecting to them. Now let's talk about the lifecycle of an MCP session. The client connects. The initialization handshake happens. The client requests the list of available tools, resources, and prompts. The server responds with the catalog. The agent reasons about what it needs. It invokes tools. It reads resources. It may request prompts, and when the work is complete, the session closes. Throughout this lifecycle, the protocol maintains state. The server knows which client it's talking to. The client knows which capabilities the server offers. And both sides can send notifications, not just requests and responses. Notifications are one-way messages. A server might notify the client that a resource has changed, prompting the agent to refresh its context. A client might notify the server that it's shutting down, allowing the server to clean up resources. This event-driven pattern keeps agents working with current context rather than stale snapshots. When a SharePoint document is updated, the MCP server can notify all connected agents that the resource has changed. The agents pull the new version and update their reasoning. The message format itself is worth understanding because you'll see it in logs, traces, and debugging sessions. A JSON-RPC request is a JSON object with 4 fields. JSON-RPC is always 2.0. ID is a unique identifier that the client generates so it can match the response to the request. Method is the capability being invoked, like tools call or resources read. And params is an object containing the method-specific parameters. A JSON-RPC response is similarly structured. JSON-RPC is 2.0, ID matches the request, and result contains the response data. If something goes wrong, result is replaced by error, which contains a numeric code, a message string, and optional data with additional context. This format is intentionally simple. You can read it in a text editor, you can parse it with any JSON library, and you can trace it through network logs without specialized tools. The initialization handshake uses the same format. The client sends an initialize request with method initialize and params containing protocol version, capabilities, and client info. The server responds with a result containing the server's protocol version, capabilities, and server info. Only after this exchange does the client send an initialized notification, and only after that notification does the server accept normal requests. This sequence matters for debugging. If your agent can't discover tools, the first thing to check is whether the initialization handshake completed. Look for the initialize request in your logs. Look for the response. Check that the protocol versions are compatible, and verify that the initialized notification was sent. Most connection failures happen at this layer, not at the tool invocation layer. The protocol version evolution is worth tracking because it affects what you can build. Version 2025-06-18 added structured tool output, elicitation support, and enhanced security. Elicitation is a pattern where a tool can ask the client for additional information before completing its execution. Instead of failing when a required parameter is missing, the tool can prompt the client to provide it. Version 2025-11-25, which the C SDK v1.0 targets, refined these patterns and added richer metadata for tools and resources. It also formalized the authorization flows that secure connections between clients and servers. As an architect, you need to decide which protocol version to target. The general rule is this: target the oldest version that supports all the features you need. This maximizes client compatibility. If you don't need structured tool output, targeting an older version means more clients can connect. If you do need it, targeting 2025-06-18 or later is the right call. The C SDK handles much of this negotiation automatically, but you need to understand the trade-offs because they affect your server design. Building your first MCP server in C theory is fine, but let's look at what this actually looks like in C bar. Microsoft's official C SDK for Model Context Protocol is available on NuGet. The package is called Model Context Protocol, and as of March 2026, the current version is 1.4. The source is on GitHub at github.com Model Context Protocol C# SDK, and it's actively maintained in collaboration with Microsoft. This isn't a community wrapper around the protocol, it's the official SDK. And version 1.0, released in March 2026, marks the point where the API surface is stable enough for production use. Let's walk through building a simple MCP server from scratch. You start with a standard .NET project, console application for local testing, web API project for remote deployment. The SDK supports both. You add the NuGet package, Model Context Protocol. That's the only required dependency for a basic server. Then you define your tools. A tool in the C SDK is a method decorated with attributes that describe its name, description, and parameter schema. The SDK uses source generators to inspect these attributes at compile time and build the protocol metadata automatically. Here's the pattern. You create a class that holds your business logic. You add a method that performs the operation your agent needs. You decorate it with the MCP tool attribute. You define the parameters as a strongly typed record or class. And the SDK generates the JSON schema for you. This means you don't write JSON schema by hand, you write CS types. The SDK reflects over them and produces the schema that the agent sees during discovery. When the protocol evolves and new schema features are added, the SDK updates its generation logic. Your code stays clean. The method body is standard C #. You can inject services through dependency injection. You can call your existing business layers. You can query databases. You can invoke other APIs. The tool method is just a normal C SaaS method that happens to be exposed through the MCP protocol. This is where the SDK's hosting extensions shine. In a typical ASP.NET Core application, you configure the host builder. You register your services in the dependency injection container, and then you call add MCP server to add the MCP server to the host. You configure it with the protocol version you want to target. You register your tool classes, and you map the MCP endpoints. The SDK handles the initialization handshake. It processes the JSON-RPC messages. It routes tool invocations to the correct methods. It serializes the responses, and it manages the session lifecycle. For local development, you run the server as a console application using STDIO transport. The agent connects to the standard input and output streams. There's no network configuration, no firewall rules, no SSL certificates. It's just a process that speaks JSON-RPC over pipes. This is perfect for rapid iteration. You write a tool, you test it with an MCP client, you see the results immediately. You iterate on the parameter schema, you refine the description, and once it's working, you graduate to a remote transport. Let's talk about structured output in practice. Before the 2025-0618 protocol update, your tool methods probably returned strings. You formatted the result as text and the agent passed it. Now you can return typed objects. You define a CPARTS record that represents your result. You populate it with data from your business system. You return it from your tool method. The SDK serializes it to JSON automatically. And the agent receives a structured object it can reason over natively. If your inventory query returns a list of stock items, you define a stock item record with fields for product ID, quantity, location, and last updated. The agent doesn't need to pass text to find the quantity. It accesses the quantity field directly in its reasoning. This is a subtle change with massive implications. It means your agents can make precise decisions based on typed data. They can compare quantities, they can check dates, they can filter lists, and they can do all of this without you writing custom parsing logic. The SDK also supports elicitation. Elicitation is a pattern where a tool can request additional input from the agent during execution. Instead of throwing an exception when a required parameter is missing, the tool returns an elicitation response. The agent sees the request, asks the user for the missing information, and provides it in a follow-up call. This creates a conversational interaction pattern. The agent doesn't need to know everything up front. It can discover what's needed as it goes. And the user experience feels natural because the agent asks clarifying questions rather than failing silently. Error handling in the SDK follows the JSON-RPC specification. When a tool throws an exception, the SDK catches it and returns a JSON-RPC error response with an appropriate error code. You can customize this behavior by implementing your own error handling middleware. The SDK also integrates with standard net logging. Every request, every tool invocation, every error is logged through the iLogger pipeline. This means your existing logging infrastructure, whether it's Application Insights, Serolog, or another provider, captures MCP activity without custom code. And there's one more feature that matters for enterprise deployments: long-running requests. Some tools take time. A report generation query might run for 30 seconds. An approval workflow might wait for a human response. The SDK supports long-running tool executions through asynchronous patterns. The client can poll for status, or the server can send progress notifications while the work continues. This prevents timeouts on slow operations. It keeps the agent informed about what's happening, and it allows your MCP servers to integrate with human-in-the-loop processes that are common in enterprise workflows. So the development workflow looks like this. You scaffold a .NET project, you add the Model Context Protocol NuGet package. You define your tools as CAS methods with typed parameters. You configure the host with add MCP server. You register your tools. You run locally with STDIO transport. You test with an MCP client. And when you're ready for production, you switch to streamable HTTP and deploy to Azure. Let's look at what the CL code actually feels like. A tool method is a standard C+ method decorated with an attribute. The method might be called getInventoryAsync. It might take a product ID string parameter and a location code string parameter. It returns a task containing an inventory result record. The inventory result has fields for quantity, last updated, and status. The attribute on the method provides the MCP-facing metadata, the tool name, the description that the agent will read during discovery, and hints about when the agent should invoke it. The SDK's source generator reads this attribute at compile time and produces the JSON schema that gets sent to clients during initialization. The parameters are defined as a CR record or class. Each property becomes a parameter in the JSON schema. Property types map to JSON schema types. String becomes string, int becomes integer, bool becomes boolean, datetime offset becomes string with format datetime, and nullable properties become optional parameters. This type-driven approach means your tool contract is defined in CFOSIT, not in JSON. When you rename a property, the schema updates automatically. When you add a new property, the schema includes it. When you change a type, the schema reflects the new type. There's no separate OpenAPI document to maintain, no manual schema editing, and no risk that your code and your schema drift out of sync. The dependency injection integration means your tool methods can request services through constructor injection or method parameters. If your tool needs to query a database, you inject the database context. If your tool needs to call another API, you inject the HTTP client. If your tool needs to read configuration, you inject iConfiguration. This is standard ASP.NET Core dependency injection, the same patterns you use in controllers, background services, and middleware. MCP servers are just another host in your ASP. Netcore application. The SDK also supports testing through the MCP server abstraction. You can create an in-memory MCP server in your unit tests, you register your tools, you send JSON-RPC requests, you verify the responses. And you test error handling, edge cases, and schema validation without running the full web host. This testability is important because MCP servers are infrastructure. They need the same testing rigor as any other production service. Unit tests for business logic, integration tests for database queries, end-to-end tests for the full JSON-RPC pipeline. The SDK's logging integration is equally straightforward. Every JSON-RPC request is logged at the information level. Every tool invocation is logged with the method name and the duration. Every error is logged with the exception details and the JSON-RPC error code. And because it uses the standard iLogger interface, your existing logging providers capture everything without configuration changes. For local testing, the SDK includes a built-in STDIO transport. You run your console application, the SDK listens on standard input, it processes JSON-RPC messages, it routes them to your tools, and it writes responses to standard output. This means you can test your server using any MCP client that supports STDIO, including the reference client from the MCP project. The transition from STDIO to streamable HTTP is a single configuration change. In your host setup, you switch from use STDIO transport to use streamable HTTP transport. You configure the HTTP endpoint, you add authentication middleware, and everything else stays the same. Your tools don't change. Your business logic doesn't change. Your dependency injection setup doesn't change. This transport abstraction is one of the SDK's strongest features. It lets you develop locally with the simplest possible transport and deploy to production with the most robust transport without rewriting your server. That's the core pattern, and it scales from a single tool on your laptop to hundreds of tools across a distributed Azure architecture. Transport layers from STDIO to streamable HTTP. Local STDIO testing is fine for your laptop, but production is a completely different conversation, and the transport you choose will determine whether your MCP deployment succeeds or fails at enterprise scale. Let's look at the 3 transports MCP supports and understand why the protocol deprecated one of them. STDIO is the simplest transport. Standard input and output. Your MCP server runs as a local process. The agent, which is also a local process, connects to the server's STDN and STDIO streams. Messages are JSON-RPC objects delimited by new lines. This transport has exactly one advantage: simplicity. There are no network stacks, no port bindings, no SSL certificates, no firewall rules. You run the server executable and the client connects automatically. It's perfect for development, it's perfect for testing, and it's perfect for local tooling scenarios where the server and client are on the same machine. But STDIO has exactly one massive limitation: it only works locally. You cannot run an STDIO MCP server on Azure and connect to it from Copilot Studio. You cannot host it in a container and expose it to remote clients. STDIO is a single process, single machine transport, and that makes it unsuitable for production deployments. Then MCP added server-sent events. SSE was the first remote transport. It uses an HTTP connection where the server can push updates to the client. The client opens a connection, the server keeps it open, and whenever the server has data to send, it pushes it through the open channel. SSE solved the remote connectivity problem. You could host an MCP server on a remote machine, clients could connect over HTTP, and the server could push real-time updates without the client constantly polling. But SSE introduced new problems. Authentication was difficult. Because SSE connections are long-lived, standard HTTP authentication mechanisms don't fit cleanly. Bearer tokens expire, sessions need refresh logic, and the long-lived connection makes token renewal awkward. CORS policies were problematic. Cross-origin resource sharing is a standard browser security feature. But SSE connections often run afoul of CORS configurations, especially in enterprise environments where strict security policies are the norm. Firewalls and proxies sometimes buffer SSE connections. This creates latency. Messages arrive late or in bursts, and some corporate proxies drop long-lived connections entirely, causing intermittent failures that are hard to diagnose. So the MCP specification deprecated SSE and replaced it with streamable HTTP. Streamable HTTP is a fundamentally different approach. Instead of maintaining a single long-lived connection, it uses standard HTTP post and GET requests. The client sends requests as post operations. The server responds immediately or streams the response over the same connection. If the server needs to send notifications, the client opens a GET connection that the server can write to. This means streamable HTTP works with standard HTTP infrastructure. Load balancers handle it. Firewalls understand it. CORS policies apply cleanly, and authentication is straightforward because every request is independent and can carry its own auth tokens. For Microsoft environments, this is the transport you want. Streamable HTTP integrates with Microsoft Entra authentication. Every post and GET request can include a bearer token from Entra ID. Conditional access policies apply per request. Multi-factor authentication can be enforced at the API gateway level. And session management follows patterns that Microsoft security teams already understand. Streamable HTTP also supports session management. When a client connects, the server can assign a session identifier. Subsequent requests include this identifier, allowing the server to maintain state across multiple HTTP requests. This is how an MCP server remembers what tools it has exposed, what resources are available, and what notifications the client has subscribed to. For Azure deployments, streamable HTTP is the natural fit. Azure Functions can handle streamable HTTP requests through HTTP triggers. An agent sends a post to your function endpoint. The function processes the JSON-RPC request and returns the response. If the operation is long-running, the function can return an accepted status and send the final result through a callback or a subsequent GET request. Azure API Management sits in front of your MCP servers and provides unified routing, rate limiting, and monitoring. You can expose multiple MCP servers through a single API management gateway. The gateway handles authentication, throttling, and request transformation, and your backend servers focus on business logic. Azure Container Apps can host persistent MCP servers that need stateful session management. If your server maintains long-lived connections to backend systems, or if it needs to cache resource data between requests, a containerized deployment gives you the control you need. And Azure Front Door or Application Gateway can distribute MCP traffic across multiple regions, providing geographic redundancy and failover. The choice between transports is not really a choice anymore. STDIO for development, streamable, HTTP for production. SSE is deprecated and should not be used for new deployments. If you have existing SSE deployments, you should plan a migration to streamable HTTP. The protocol changes are not dramatic. The JSON-RPC message format is the same, but the connection model shifts from persistent streams to request-response pairs, and that shift unlocks enterprise-grade authentication, scaling, and monitoring. Here's the decision matrix. If you're building a local tool or a developer utility, use STDIO. It's the fastest path to a working server. If you're deploying to Azure, use streamable HTTP. It's the only transport that integrates cleanly with Entra, API Management, and standard enterprise security policies. If you're evaluating SSE for a new project, stop. Use streamable HTTP instead. SSE is deprecated in the MCP specification and will not receive further enhancements. This transport decision is one of the most important architectural choices you'll make. Because once you have hundreds of agents connecting to dozens of MCP servers, the transport layer determines your authentication model, your scaling strategy, and your observability footprint. Get this right, and the rest of your MCP architecture follows cleanly. Get this wrong, and you'll be fighting connection issues, auth failures, and firewall rules while your AI team waits for the connectivity layer to work. The USB-C for AI pattern, why standardization wins. This is where the USB-C for AI analogy starts to make real sense. Not as a marketing phrase, as a structural pattern. Before USB-C, every device had its own cable, its own connector, its own pinode. You needed a drawer full of adapters just to connect a phone, a laptop, and a monitor. The connections worked, but they were bespoke, fragile, and every new device added another cable to the pile. That's where we are with AI integrations today. Every business system has its own API, its own auth model, its own payload format, its own error handling. And every AI agent that needs to talk to those systems needs custom code for each connection. A custom wrapper for the ERP, a custom connector for the CRM, a custom pipeline for the SharePoint search. And when any of those systems upgrade, the custom code breaks. MCP is the USB-C moment for AI connectivity. One protocol, one discovery model, one capability contract. And any agent that speaks MCP can connect to any MCP server without knowing what backend system it wraps. This standardization unlocks something bigger than convenience. It unlocks composability. When every integration is bespoke, you can't compose them. Your inventory agent knows how to talk to your ERP because you wrote that wrapper, but your customer service agent doesn't know how to talk to your inventory system because it uses a different wrapper with a different interface. The knowledge doesn't transfer. With MCP, every agent speaks the same protocol. When you build an MCP server for your ERP, any agent can use it. The inventory agent, the customer service agent, the finance agent, the procurement agent, they all discover the same tools, they all invoke them through the same contract, and they all receive structured responses they can reason over. This is the digital twin pattern. Instead of writing integration code for every agent, you codify your business logic into an MCP server. The server knows your approval hierarchy, it knows your discount rules, it knows your compliance checks, it knows which orders need manager approval and which can auto-approve. It knows which customers get expedited shipping and which regions have export restrictions. The AI doesn't need to guess how your business works. It asks the MCP server, and the server provides the answer through a structured, typed contract. This changes the economics of AI deployment. Without MCP, every AI project starts with integration. 6 months of wrapper development before the agent can do anything useful. With MCP, you build the server once. You expose your business capabilities as tools, and every subsequent AI project inherits that connectivity for free. The organizations that will dominate the agentic era are the ones that invest in their MCP layer first, not because the protocol is exciting, but because it compounds. Every agent you deploy gets cheaper, Every integration gets faster, and your AI strategy stops being a collection of brittle point-to-point connections and starts being a composable capability platform. That's why Microsoft is betting on MCP, not as a feature, as a foundation, from local dev to Azure production. Let's get specific about Azure, because this is where most architects get stuck. They build a beautiful MCP server on their laptop. It works in STDIO mode. The local agent discovers the tools. The tool calls return perfect structured data. And then they try to deploy it to Azure and everything falls apart. Not because Azure is hard, but because the mental model changes. Local development is about getting it working. Production deployment is about keeping it working at scale. Let's walk through the Azure deployment patterns that make sense for MCP servers. Azure Functions is the simplest starting point for most use cases. You write an HTTP triggered function that receives MCP requests and returns MCP responses. The function's runtime handles scaling, load balancing, and monitoring. You pay per execution, and when nobody is using your MCP server, it scales to 0. This is ideal for MCP servers with sporadic usage patterns. A server that handles approval workflows might only receive a few hundred requests per day. Running it on functions means you don't pay for idle capacity. And when usage spikes, function scales automatically. The implementation pattern is straightforward. Your function receives an HTTP post containing a JSON-RPC request. It passes the method name and parameters. It routes to the appropriate tool handler. It executes the business logic. It serializes the result. And it returns an HTTP response with the JSON-RPC response object. For streamable HTTP, you need to handle session management. When a client initializes a connection, you assign a session identifier. You store the session state in Azure Cache for Redis or Cosmos DB. Subsequent requests include the session ID, and your function retrieves the state to continue the conversation. Azure Container Apps is the next step up. If your MCP server needs persistent state, long-running connections, or complex dependency graphs, functions might feel constraining. Container Apps gives you a fully managed Kubernetes-like environment without the Kubernetes complexity. You containerize your MCP server application. You define the container image, the resource requirements, and the scaling rules. Azure deploys it, monitors it, and scales it based on HTTP request volume or custom metrics. Container Apps is ideal when your MCP server maintains a connection pool to backend databases, when it caches resource data in memory for fast access, or when it needs to run background tasks alongside the main request processing. Azure API Management sits in front of both. You don't want to expose your MCP servers directly to the internet. You want a gateway. API Management provides that gateway. It handles authentication at the edge. It validates bearer tokens against Microsoft Entra. It applies rate limiting to prevent abuse. It transforms requests if your backend servers need a different format. And it logs every request for auditing and monitoring. With API Management, you can publish multiple MCP servers through a single endpoint. The client connects to one URL. API Management routes the request to the appropriate backend based on the path, the headers, or the payload content. You can add new MCP servers without changing the client configuration. You can update backend servers without taking down the gateway. This is the pattern you want for multi-server deployments. Azure Key Vault stores your secrets. MCP servers need connection strings to databases. They need API keys for third-party services. They need certificates for mutual TLS. You don't hard-code these in your application. You store them in Key Vault. Your application reads them at startup, and when a secret rotates, you update it in one place without redeploying your code. Application Insights provides observability. Every MCP request, every tool invocation, every error is logged to Application Insights. You see request latency. You see error rates. You see which tools are called most frequently. You see which agents are generating the most load. And you can set up alerts for anomalous patterns. This observability is critical because MCP servers are infrastructure. When they fail, agents fail. And when agents fail, users notice. You need monitoring that tells you something is wrong before the users do. For network isolation, VNet integration keeps MCP traffic inside your network boundary. Your MCP servers run in a subnet that has no public internet access. API Management has a private endpoint in the same VNet. Agents connect through the private endpoint. The traffic never traverses the public internet. And your network security team can apply the same policies they use for every other internal API. For scaling patterns, you need to match the Azure service to the workload shape. Azure Functions with a consumption plan is ideal for bursty, low-frequency workloads. If your agents invoke tools sporadically, consumption plan means you pay nothing during idle periods and scale automatically when traffic arrives. But cold start latency can be several seconds for complex applications. If your agents are interactive, those seconds matter. For interactive agents that need sub-second responses, use Azure Functions with a premium plan. Premium plan keeps instances warm. It eliminates cold start latency. And it supports VNet integration for private connectivity. The trade-off is cost. You pay for the warm instances even when idle. Azure Container Apps is the middle ground. It scales to 0 like consumption functions, but it warms containers faster than functions because the container image is already pulled and the runtime is already initialized. For MCP servers that need persistent state or complex dependency graphs, container apps is often the right choice. For very high throughput, consider Azure Kubernetes Service. AKS gives you full control over the orchestration layer. You define the pod specifications, you configure the horizontal pod autoscaler, you manage the node pools, and you optimize every layer of the stack for your specific latency and throughput requirements. The trade-off is operational complexity. AKS requires Kubernetes expertise, and it requires ongoing cluster management. Most MCP deployments start with functions or container apps and graduate to AKS only when the workload demands it. For deployment automation, Azure DevOps and GitHub Actions both support CI/CD pipelines for MCP servers. You commit code. The pipeline builds the project, it runs unit tests, it packages the application, it deploys to a staging environment, it runs integration tests against a real MCP client, and if everything passes, it deploys to production. Blue-green deployment is the pattern you want for zero downtime updates. You run two identical environments. Blue is production, green is staging. When you deploy a new version, you push it to green. You verify it works, you switch the API management routing from blue to green. And the old version stays running as a hot standby until you're confident the new version is stable. This matters for MCP because agents maintain session state. If you restart a server mid-session, the client loses its context. It has to reinitialize. It has to rediscover tools. And if the new server version has different capabilities, the agent's reasoning might change unexpectedly. Blue-green deployment avoids this. The switch happens at the routing layer. Active sessions stay on the old version. New sessions go to the new version. And after a grace period, you retire the old version. That's the Azure deployment pattern. Functions or container apps for compute, API management for the gateway, Key Vault for secrets, application insights for monitoring, VNet integration for security, CI/CD for deployment, blue-green for updates. It's not exotic, it's standard Azure architecture applied to a new protocol. And that's the point. MCP doesn't require you to invent new infrastructure patterns. It fits into the patterns you already know. Connecting Copilot Studio to MCP servers. Now let's look at where MCP meets the tools your users already know. Copilot Studio, Microsoft Copilot Studio added Model Context Protocol support and took it to general availability in March 2026. This wasn't a quiet feature launch, it was a signal. Microsoft is treating MCP as a first-class integration pattern for business agents. The GA release included 3 capabilities that matter for architects. Tool listing. Your Copilot Studio agents can discover and display tools from connected MCP servers. When an agent initializes, it queries the MCP server for its tool catalog. Each tool appears in the agent's reasoning pipeline with its description and parameter schema. The agent decides which tools to invoke based on the user's intent. Enhanced tracing. When an agent invokes an MCP tool, Copilot Studio logs the request, the parameters, the response, and any errors. This isn't just debugging information, it's audit data. You can see which agents called which tools. You can trace a user's request through the entire chain of tool invocations. And you can identify which tools fail most frequently. Scalable deployment infrastructure. The GA release added backend improvements that let Copilot Studio handle large numbers of concurrent MCP connections. This matters because enterprise agents serve thousands of users simultaneously. If the MCP integration was built for demo-scale loads, it would collapse in production. The GA release is built for production scale. Connecting an MCP server to Copilot Studio is a configuration task, not a development project. You provide the server endpoint, you configure the authentication method, typically a Microsoft Entra service principal or an API key stored in Key Vault. You set the protocol version you want to use, and Copilot Studio handles the rest. The agent discovers the tools automatically. It adds them to its reasoning context, and when a user asks a question that requires tool access, the agent invokes the appropriate tool through the MCP protocol. This means your existing Copilot Studio agents get new capabilities without rewriting them. If you build an MCP server that exposes inventory lookup, every Copilot Studio agent you connect to that server can now check inventory. If you add a tool for approval workflow status, every agent can now track approvals. If you add a tool for document generation with sensitivity labels, every agent can now draft compliant documents. The agents don't change, the MCP server changes. And the agents inherit the new capabilities through discovery. Microsoft also published a Model Context Protocol lab on GitHub in April 2025. This is a hands-on repository with sample servers, client configurations, and exercises specifically for Copilot Studio. If you're evaluating MCP for your organization, start here. The lab gives you a working end-to-end connection in under an hour, and the integration goes beyond Copilot Studio itself. Dynamics 365 Finance and Operations added MCP server support in April 2026. This means you can extend your ERP agents with custom tools through the same protocol. Your supply chain agent can query an MCP server that knows your custom procurement rules. Your finance agent can invoke tools that understand your chart of accounts structure. Your manufacturing agent can check production schedules through tools that integrate with your shop floor systems. This isn't a replacement for Dynamics 365's native capabilities. It's an extension pattern. Dynamics provides the standard ERP functions. MCP servers provide the custom business logic that makes your ERP fit your organization's specific processes. And agents combine both through a single reasoning pipeline. The practical workflow for an architect looks like this. You identify the gaps in your current Copilot agents. What questions do users ask that the agents can't answer? What actions do users request that require back-end system access? You catalog these gaps. You prioritize them by business impact. And for each priority gap, you build an MCP tool. Then you deploy the MCP server to Azure. You register it in Copilot Studio. You test the agent's behavior with the new tools. You refine the tool descriptions so the agent knows when to invoke them. You tune the parameter schemas so the agent provides the right inputs. And you monitor the tool usage to see which ones deliver value. This is an iterative cycle, not a big bang integration project. You start with one tool, one server, one agent. You prove the pattern works, then you expand. The configuration details in Copilot Studio are worth understanding because they're not obvious from the documentation. When you register an MCP server, you provide the endpoint URL. This is the URL of your Azure function, container app, or API management gateway. Not the direct backend server URL if you're using a gateway. The agent talks to the gateway. The gateway talks to the server. You also provide the authentication configuration. There are two common patterns. The first is Microsoft Entra service principle. You register an app in Entra. You grant it permissions. You create a client secret or a certificate. And you configure Copilot Studio to acquire tokens using that service principle. The second pattern is API key. You generate a key in Azure API Management or in your server's key store, and you configure Copilot Studio to send that key in the authorization header. The service principle pattern is more secure. The API key pattern is simpler. For production, use service principles. For prototyping, API keys are acceptable if you rotate them before going live. You also set the protocol version. Copilot Studio supports multiple protocol versions. You set the version that matches your server. If your server implements 2025-1125, you set that in Copilot Studio. If your server implements 2025-0618, you set that. The client and server negotiate capabilities within that version, but the version setting tells Copilot Studio what message format to expect. After registration, Copilot Studio performs a discovery call. It sends an initialized request to your server. It requests the tool catalog, and it populates the agent's reasoning context with the available tools. This discovery happens at agent startup or when you manually refresh the connection. If discovery fails, the tools don't appear, and the agent behaves as if the server doesn't exist. This is usually an authentication problem. The service principal might not have permission. The API key might be wrong. The network firewall might block the connection, or the server might be down. Debugging discovery failures requires checking three things: the network path, the authentication token, and the server's initialization response. Application insights. Logs on the server side show the incoming requests. Entra sign-in logs show the token acquisition attempts. And Copilot Studio's connection test shows the discovery result. Once discovery succeeds, testing is straightforward. You open the agent in test mode. You ask a question that requires the new tool. You watch the agent's reasoning trace. You see which tools it considers. You see which tool it selects. You see the parameters it provides, and you see the response it receives. If the agent selects the wrong tool, your tool description is probably too vague. If the agent provides wrong parameters, your parameter schema might be too complex or poorly named. If the agent ignores the tool entirely, it might not recognize that the user's question maps to the tool's capability. Tuning is iterative. You adjust the description, you test again, you rename a parameter, you test again, you add an example to the description, you test again. Each cycle takes minutes. And after a few cycles, the agent invokes the tool reliably. This tuning process is one of the most important skills for MCP architects, because a perfectly built server is useless if the agent doesn't know when to use it. Work IQ, the intelligence layer, and MCP server, but Copilot Studio is only half the story. The real power is what your agents can understand about your business, and that's where Work IQ comes in. Work IQ is Microsoft's intelligence layer for the agentic era. It's the semantic engine that reads everything happening across your Microsoft 365 environment and turns it into context that agents can reason over. SharePoint documents, OneDrive files, Teams conversations, email threads, meeting transcripts, calendar events, planner tasks, loop pages. WorkIQ understands the relationships between all of these. It knows that a Teams conversation is about a project that has a SharePoint site that contains a document that was discussed in a meeting that was scheduled by someone who reports to a manager who approved the budget. That's not keyword search, that's semantic understanding. And Microsoft open-sourced a WorkIQ MCP server on GitHub at github.com Microsoft WorkIQ. This means any agent that speaks MCP can access WorkIQ context, not just Copilot, not just Microsoft agents, any MCP-compatible client. The WorkIQ MCP server exposes 6 core tools. It can retrieve organizational context, who works on which team, who reports to whom, what projects are active, what goals are being tracked. It can pull document content from SharePoint and OneDrive with full semantic understanding. It can read Teams conversations and email threads and extract the key decisions and action items. It can access meeting transcripts and identify who committed to what. It can query calendar data and understand availability patterns. And it can draft Word documents that carry your existing sensitivity labels and compliance metadata. This last point is critical for enterprise deployments. When an agent drafts a document through WorkIQ, the resulting file inherits the sensitivity label from the template or the parent folder. If the document contains financial data, it gets the confidential label automatically. If it contains public marketing content, it gets the public label. The agent doesn't need to understand your data classification scheme. WorkIQ applies it through the existing Microsoft Purview policies. WorkIQ also supports multiple protocols. The REST API gives you raw access. The A2A protocol lets agents delegate tasks to WorkIQ as a peer, and the MCP protocol lets agents discover WorkIQ capabilities as tools and invoke them through the standard JSON-RPC contract. For architects, the MCP integration is the most important because it means WorkIQ becomes just another MCP server in your architecture. Your agents don't need custom code to talk to WorkIQ. They use the same protocol they use for every other server. They discover WorkIQ tools during initialization. They invoke them through the same request pipeline, and they receive structured responses through the same deserialization logic. This uniformity is what makes MCP powerful at scale. Your agents don't care whether a tool talks to SharePoint, SQL Server, or an internal line of business application. They see a capability catalog, they select a tool, they provide parameters, they receive results. WorkIQ is the tool that gives your agents organizational memory. Without WorkIQ, your agents reason in isolation. They answer based on the prompt and their training data. They don't know what your team discussed in yesterday's meeting. They don't know that the project charter was updated last week. They don't know that the budget was reallocated in the quarterly review. With WorkIQ, they do. And because WorkIQ updates in real time, your agents are always working with current context. When a document changes, WorkIQ sees the change. When a meeting ends, WorkIQ processes the transcript. When an email arrives, WorkIQ extracts the action items. Your agents don't just have access to your business data, they have access to your business reality. A2A protocol agent-to-agent orchestration. But what happens when you need multiple agents to work together? Because most real-world problems don't fit inside a single agent. A customer service request might require an agent that understands the customer's history, an agent that checks inventory levels, an agent that verifies pricing rules, and an agent that generates a quote. Each agent has its own expertise, its own tools, its own context, and they need to collaborate. This is where A2A comes in. A2A stands for Agent-to-Agent Protocol. Google launched it in April 2025 as an open standard for AI agent communication. Microsoft announced support for A2A in May 2025, and in June 2025, Google donated A2A to the Linux Foundation, where it now lives as a vendor-neutral project with founding members, including AWS and Cisco. A2A is not a competitor to MCP. It solves a completely different problem. MCP connects agents to tools. A2A connects agents to agents. You need both. A2A defines 3 core concepts that enable agent collaboration. Agent cards are how an agent advertises its capabilities. When an A2A-compatible agent starts up, it publishes an agent card that describes what it can do, what inputs it accepts, what outputs it produces, and what authentication it requires. Other agents can discover this card and decide whether to delegate work to it. Tasks are the work units that agents exchange. When one agent needs another agent to do something, it creates a task. The task includes the goal, the context, and any constraints. The receiving agent processes the task and returns updates, results, or requests for additional information. The transport layer uses HTTP and JSON-RPC 2.0, which means it aligns with the same infrastructure patterns as MCP. In fact, as streamable HTTP becomes the standard transport for MCP, the 2 protocols may converge on the same underlying connection model. The relationship between MCP and A2A is complementary and hierarchical. At the bottom, you have your business systems, ERP, CRM, SharePoint, databases. MCP servers expose these systems as tools. Individual agents consume those tools through MCP to perform their specialized functions. And A2A enables those specialized agents to collaborate on complex tasks that span multiple domains. In a Microsoft environment, this pattern is emerging rapidly. A Copilot Studio agent might receive a user request. It uses MCP to query WorkIQ for organizational context. It uses A2A to delegate subtasks to specialized agents. One specialized agent checks inventory through an MCP server. Another verifies pricing through a different MCP server. A third generates the quote document through WorkIQ. The Copilot Studio agent orchestrates. The specialized agents execute. The MCP servers provide the tools, and A2A provides the coordination language. Microsoft's support for A2A, announced in May 2025, signals that this multi-agent pattern is part of their long-term vision. They're not just building a single agent that does everything. They're building an ecosystem where agents specialize, collaborate, and compose their capabilities through open protocols. For architects, this means your connectivity layer needs to support both protocols. You need MCP servers that expose your business capabilities as tools. You need agents that consume those tools to perform specialized functions. And you need A2A infrastructure that lets those agents discover each other, delegate tasks, and share results. The good news is that both protocols use the same foundational technologies: HTTP, JSON-RPC 2.0, standard authentication, Azure hosting, Entra identity. The infrastructure you built for MCP is largely reusable for A2A. The Linux Foundation governance of A2A is also important because it means A2A isn't controlled by Google or Microsoft or any single vendor. It's an open standard with a neutral governance model. This reduces vendor lock-in risk, it encourages broad adoption, and it means the protocol will evolve based on community needs rather than a single company's roadmap. That's the emerging architecture: MCP for tools, A2A for agents. Together, they form the connectivity fabric of the agentic era. The practical implementation pattern for A2A in Microsoft environments is still emerging, but the trajectory is clear. Copilot Studio agents will act as orchestrators. They will receive user requests, decompose them into subtasks, and delegate those subtasks to specialized agents through A2A. The specialized agents will execute their tasks using MCP tools, and the results will flow back through A2A to the orchestrator, which synthesizes the final response. This means your architecture needs to support both protocols from day one. Even if you only have one agent today, you need to design for the day when you have 10. Because adding A2A to an architecture that was only designed for MCP is harder than designing for both from the start. The shared foundation helps. Both protocols use HTTP, both use JSON, both authenticate through Entra, and both can route through API management. So the infrastructure investment is unified. The protocol diversity is at the application layer, not the network layer. Security and identity, Entra Agent ID and Agent 365. All of this connectivity is useless if it's not secure, and the old security model doesn't fit. Here's the problem that most organizations haven't confronted yet. Your existing identity and access management was designed for humans. A human user has a single identity in Microsoft Entra ID. They sign in with a password or a passkey. They get a token. That token grants them access to SharePoint, Teams, Outlook, and whatever other resources their role allows. Conditional access policies check their location, their device compliance, and their risk score before granting access. This model works because humans are predictable. They log in once per session. They access resources at human speed. They read documents, write emails, and attend meetings. Their behavior follows patterns that security systems can baseline and monitor. AI agents break every one of these assumptions. An agent doesn't log in once per session. It authenticates before every tool invocation. It might make 100 requests in a minute. It doesn't read documents. It extracts structured data and reasons over it. It doesn't have a manager who can approve access requests. And its behavior doesn't follow human patterns, so traditional anomaly detection flags it as suspicious. This is the identity gap, and Microsoft recognized it. Microsoft Entra Agent ID is the identity and security framework that Microsoft built specifically for AI agents. It launched in early 2026, and it's not an incremental update to existing Entra features. It's a new layer designed from the ground up for non-human identities that operate at machine speed and machine scale. Agent ID lets you build, discover, govern, and protect agent identities at enterprise scale. When you create an agent in Copilot Studio or register a custom agent, you assign it an Agent ID identity. This identity is distinct from human user identities and distinct from traditional workload identities like service principals. It has its own lifecycle, its own permissions, its own audit trail, and it can be governed. Agent ID includes agent sprawl detection. It scans your environment and identifies every agent that has been registered, including the ones that were created for a pilot 6 months ago and never decommissioned. It shows you what each agent can access. It flags agents with excessive permissions. And it alerts you when an agent's behavior deviates from its baseline. This matters because abandoned agents are attack vectors. An agent that was created for a summer interns project and forgotten about still has its credentials, still has its permissions, and still has access to whatever data it was granted 6 months ago. If an attacker discovers that agent's credentials, they have a trusted identity with legitimate access to your systems. Agent sprawl detection finds these forgotten identities before attackers do. Then there's Microsoft Agent 365. Agent 365 is the control plane for AI agents across your Microsoft 365 environment. It extends the same Microsoft 365 and Microsoft security controls you already use for human users to the agentic layer. Observe. You see what every agent is doing, what tools it's invoking, what data it's accessing, and what decisions it's making. Govern. You set policies that control which agents can access, which MCP servers, which tools they can invoke, and which data they can read. Secure. You apply the same sensitivity labels, DLP policies, and retention rules to agent actions that you apply to human actions. And in May 2026, Microsoft added conditional access for agents. Conditional access is the zero-trust engine that Microsoft has built over the past decade. It evaluates every access request against a set of conditions. Is the user coming from a managed device? Are they in a trusted location? Is their risk score acceptable? Is multi-factor authentication required? For human users, this works. For agents, it needed extension. Conditional access for agents extends these zero-trust principles to non-human identities. When an agent tries to invoke an MCP tool, conditional access evaluates the request. Is the agent coming from an approved host? Is its agent ID valid and active? Has it been flagged by agent sprawl detection? Is the requested tool within its approved scope? If any condition fails, access is blocked. This isn't an afterthought. It's a fundamental security layer, because without it, your MCP servers are exposed to any agent that can reach their endpoint. And in a world where agents authenticate at machine speed, a compromised agent can exfiltrate data at a rate that human attackers can't match. The licensing model is also important for architects to understand. Microsoft Entra Agent ID is part of the Entra ID suite, which is priced at $12 per user per month as of 2026. The suite includes 9 services, and Agent ID is one of them. This means you're not buying a standalone security product for agents. You're extending your existing identity investment to cover the agentic layer. For organizations already using Entra ID Suite, Agent ID is an incremental capability. For organizations on lower tiers, it's a reason to evaluate the suite upgrade. From an architectural perspective, the integration between Agent ID and MCP is straightforward. Your MCP server validates the Agent ID token on every request. It checks that the agent is authorized to invoke the requested tool. It logs the invocation for auditing. And it applies data classification rules based on the agent's scope rather than a human user's role. This means you can have different security policies for different agents. A customer-facing chatbot agent might have read-only access to product catalogs and order history. An internal procurement agent might have write access to purchase order systems, but no access to customer PII. A finance reporting agent might have access to aggregated data, but not to individual transactions. Each agent has its own identity, its own permissions, its own conditional access policies. And when an agent is no longer needed, you revoke its agent ID. Its permissions disappear, its access tokens expire, and it becomes a non-entity in your security posture. That's the governance layer. MCP provides the connectivity, Agent ID secures the connections, and Agent 365 provides the control plane. Together, they create an enterprise-grade architecture that doesn't just connect agents to data, it connects them safely. Architecting the complete MCP layer, reference architecture. Architecting the complete MCP layer, reference architecture. Let's put all of this together into a reference architecture you can take to your team, because theory is fine, but what your organization needs is a diagram, a data flow, a decision tree, and a clear picture of how all the pieces connect. Here's the layered architecture. At the bottom is the data layer. This is where your business systems live. Your Dynamics 365 ERP, your SharePoint sites, your SQL databases on Azure, your custom line of business applications, your OneDrive files, your team's conversations. This layer doesn't change. These are the systems you've built and bought over the past decade. They are your source of truth. Above the data layer is the MCP server layer. This is where the connectivity happens. Each MCP server wraps one or more business systems and exposes their capabilities through the standardized protocol. You might have an ERP MCP server that exposes tools for inventory checks, order creation, and supplier lookups. You might have a SharePoint MCP server that exposes resources for project documents and policy manuals. You might have a custom application MCP server that exposes tools for your proprietary business processes. Each MCP server is a net application built with the official C SDK. Each server registers its tools, resources, and prompts through the SDK's attribute system. Each server handles the JSON-RPC protocol, the initialization handshake, and the capability negotiation. And each server runs on Azure, either through Azure Functions for event-driven workloads or Azure Container Apps for persistent services. Above the MCP server layer is the intelligence layer. This is Work IQ. It sits alongside the MCP servers rather than replacing them because it serves a different purpose. While MCP servers expose business operations, Work IQ exposes organizational context. It knows who works on what. It knows what meetings decided. It knows which documents changed. And it provides this context through its own MCP server so that any agent can discover and consume it. Above the intelligence layer is the protocol layer. This is where MCP and A2A operate. MCP handles agent-tool communication. A2A handles agent-to-agent communication. Both protocols use HTTP. Both use JSON-RPC 2.0. Both integrate with Microsoft Entra for authentication. And both can route through Azure API Management for gateway services. API Management is the critical hub in this layer. It receives all incoming protocol requests. It validates bearer tokens against Entra Agent ID. It applies rate limiting based on the agent's tier. It routes requests to the appropriate backend MCP server based on the tool name or the resource URI. And it logs every request for auditing and monitoring. This means your MCP servers don't sit on the public internet. They live in a private VNet. API management has a private endpoint in that VNet. All traffic flows through the gateway, and your network security team applies the same policies to MCP traffic that they apply to every other internal API. Above the protocol layer is the agent layer. This is where your agents live. Copilot Studio agents that users interact with through Teams chat. Custom agents that run background processes. Specialized agents that handle procurement, customer service, or financial reporting. Each agent has an agent ID identity in Entra. Each agent discovers tools through MCP. Each agent delegates tasks through A2A. And each agent operates within the scope defined by its conditional access policies. At the top is the presentation layer. This is where users engage with the agents. Teams chat. Copilot in Outlook, Power Apps interfaces, custom web applications, the user asks a question. The question flows to an agent, the agent reasons, the agent discovers tools, the agent invokes tools through MCP, the tools execute business logic, the results flow back. The agent synthesizes the answer, and the user receives a response that is grounded in real-time business data. That's the vertical stack. Now let's look at the data flow horizontally. A user asks their Copilot Studio agent, what's the status of the Phoenix project, and are we on track to deliver by Friday? The agent receives the question. It initializes its MCP connections. It discovers available tools from the registered MCP servers. It sees a tool from the WorkIQ MCP server called getProjectStatus with a project name parameter. It sees a tool from the ERP MCP server called checkDeliverySchedule with a project code parameter. The agent reasons. It decides to invoke both tools. But first, conditional access evaluates the agent's identity. API Management receives the request, it validates the bearer token. It checks the agent ID against Entra Agent ID. It confirms the agent is authorized to invoke these specific tools. It checks the rate limit. And it routes the requests. The WorkIQ tool executes. It queries SharePoint for project documents. It reads Teams conversations about the Phoenix project. It checks planner tasks. And it returns a structured summary of the project status, including risk flags identified from recent meeting transcripts. The ERP tool executes. It queries the delivery schedule database. It checks inventory levels for required components. It verifies supplier lead times. And it returns a structured delivery forecast. The agent receives both results. It synthesizes them. It recognizes that while the project status is green, a supplier lead time has slipped by 2 days, putting the Friday delivery at risk. It drafts a response for the user. And it optionally triggers a notification tool to alert the project manager. The user sees a concise answer grounded in real project data and real supply chain conditions. That's not a demo, that's a production architecture. And it scales. When you have 10 users, this architecture works on a single Azure function. When you have 10,000 users, API Management distributes the load. Azure functions scale horizontally. Container apps handle persistent state. Cosmos DB caches session data. Application Insights monitors every request. And Azure Front Door routes traffic across regions. The scaling patterns are standard Azure, the protocol is standard MCP, the identity is standard Entra, and the architecture is standard enterprise integration applied to a new domain. Now let's talk about failure modes, because architects don't just design for success, they design for failure. What happens when an MCP server is down? The agent discovers the server is unavailable during initialization or receives an error during tool invocation. A well-designed agent handles this gracefully. It informs the user that a specific data source is temporarily unavailable. It falls back to alternative tools if they exist, and it queues the request for retry if the operation is critical. What happens when an MCP server is slow? API Management applies timeout policies. If a tool execution exceeds the configured threshold, the gateway returns a timeout error. The agent receives the error and decides whether to retry, to inform the user, or to proceed with partial information. What happens when an agent is compromised? Entra Agent ID detects the anomaly, conditional access blocks the request. The Agent 365 control plane alerts the security team, and the compromised agent's credentials are revoked before significant damage occurs. What happens when a tool returns unexpected data? The agent's reasoning pipeline handles the structured response. If the response doesn't match the expected schema, the agent flags the inconsistency rather than hallucinating an answer. The error is logged, the MCP server operator is alerted, and the schema is corrected. These failure modes aren't hypothetical. They're the standard resilience patterns that every enterprise architect already applies to APIs and microservices. MCP doesn't change the resilience model, it extends it to the agentic layer. Finally, let's address the anti-patterns. The most common mistake is putting business logic in the agent instead of the MCP server. The agent should reason. It should decide which tools to invoke. It should synthesize results, but it should not implement business rules. Business rules belong in the MCP server, where they can be versioned, tested, and reused across multiple agents. The second common mistake is using STDIO transport in production. STDIO is for development, streamable HTTP is for production. Deploying a STDIO server to Azure and trying to connect remotely is a category error. The third common mistake is hard-coding authentication. Every MCP server should validate tokens through Entra Agent ID, hard-coded API keys, connection strings, or credentials create security debt that will eventually cause a breach. The fourth common mistake is building one giant MCP server that exposes every tool in the organization. This creates a monolithic dependency. When that server needs maintenance, every agent that depends on it stops working. Instead, build focused MCP servers for specific domains. One for ERP, one for SharePoint, one for custom applications. This limits blast radius and enables independent deployment. The fifth common mistake is ignoring observability. MCP servers are infrastructure. They need monitoring, they need logging, they need alerting. Without application insights or an equivalent observability platform, you'll be debugging production issues in the dark. A sixth mistake is skipping capacity planning. An MCP server that handles 10 requests per minute during testing will collapse under 1,000 requests per minute when 1,000 users start using the agent simultaneously. Load test early. Understand your latency distribution, identify the P99 response time, and set your scaling rules based on real traffic patterns, not optimistic estimates. A seventh mistake is neglecting backward compatibility. When you add a new parameter to a tool, older clients might not provide it. When you rename a tool, existing agents lose access until they reinitialize. When you change a response schema, agents that depend on specific field names break. Version your tools carefully. Add parameters as optional before making them required. Deprecate tools before removing them, and communicate changes to agent owners before deployment. An eighth mistake is failing to document the server capabilities. The MCP protocol provides tool descriptions and parameter schemas, but it doesn't provide business context. An agent developer needs to know what business process a tool supports. They need to know what data quality to expect. They need to know what error conditions to handle. Write documentation that lives outside the protocol, share it with agent teams, and keep it current. A ninth mistake is deploying without a rollback plan. When a new MCP server version breaks an agent, you need to revert quickly. Blue-green deployment is the standard pattern, but it requires automation. Manual rollbacks take too long. Build the deployment pipeline before you need it. Test the rollback procedure before you deploy to production. And practice the failure recovery during planned maintenance windows. Avoid these mistakes, and you'll have an architecture that lasts. Implementation roadmap from POC to production. Knowing the architecture isn't the same as knowing where to start. So here's your 90-day roadmap from proof of concept to production. Weeks 1 and 2 are about setting up your development environment and proving the pattern works. Install the Model Context Protocol NuGet package in a new or a net console application. Build a single tool that does something simple but real. Maybe it queries your product catalog. Maybe it checks a database record. Maybe it reads a SharePoint list. The specific tool doesn't matter. What matters is that it connects to a real data source and returns real structured data. Test it locally using STDIO transport. Connect an MCP client. Verify that the client discovers the tool. Verify that tool invocation returns the expected data. Verify that the structured output matches your schema. And verify that errors are handled gracefully. This 2-week block proves the pattern. If you can't get a single tool working locally, you don't have a foundation. Fix the issues here before you try to scale. Weeks 3 and 4 are about graduating to remote transport and Azure deployment. Convert your console application to an ASP. Netcore web application. Add streamable HTTP transport using the SDK's hosting extensions. Configure authentication with the Microsoft Entra service principal. Deploy to Azure Functions. Add application insights for logging. And test the same tool through the remote endpoint. This is where most developers encounter their first real issues. Authentication configuration is tricky. Bearer token validation requires the right middleware. Course policies need to allow your client origins. And Azure Functions cold start can add latency to the first request after idle periods. Expect to spend time debugging these issues. That's normal. Document your configuration. The patterns you establish here will be replicated across every MCP server you build. Weeks 5 and 6 are about integrating with Copilot Studio. Register your MCP server endpoint in Copilot Studio. Configure the authentication method. Set the protocol version. Test the connection. Verify that your tools appear in the agent's tool catalog. And then test end-to-end with real user queries. This is where the human factor enters. Your tool descriptions need to be clear enough that the agent knows when to invoke them. If your description is vague, the agent will invoke the wrong tool or skip the right one. If your parameter schema is too complex, the agent will provide incomplete or incorrect inputs. Tune your tool descriptions, test with real user questions, iterate on the parameter schemas, and monitor the tool invocation logs to see which tools are being used and which are being ignored. Weeks 7 and 8 are about adding organizational context through WorkIQ. Register the WorkIQ MCP server in your architecture. Test the 6 core tools, verify that your agents can retrieve organizational context, read documents, access Teams conversations, and draft labeled documents. This is where your agents start feeling intelligent. Without WorkIQ, your agents answer based on the user's immediate query and whatever tool data they can retrieve. With WorkIQ, your agents understand the organizational context behind the query. They know who is involved. They know what decisions were made. They know what documents are relevant. The integration effort here is lighter than weeks 3 and 4 because WorkIQ MCP server is already built. You're configuring it, not coding it. But the organizational impact is significant because it connects your agents to the institutional knowledge that lives in Microsoft 365. Weeks 9 and 10 are about securing the architecture. Implement Entra Agent ID for every agent in your architecture. Configure conditional access policies. Set up agent sprawl detection. Define least privilege permissions for each agent. And test the security boundaries. This isn't a checkbox exercise. Invite your security team to review the architecture, show them how Agent ID works, show them how conditional access applies to agents, show them the audit logs in API Management, and get their approval before you open the system to production users. Security team buy-in is critical, because if the security team doesn't understand how agent authentication works, they will block the deployment. And if they block it after you've built everything, you've wasted 10 weeks. Get them involved early. Use this roadmap as a conversation starter. Show them week 9 and 10 during week 1. Let them shape the security architecture while you're still building the prototype. Weeks 11 and 12 are about hardening for production. Load test your MCP servers, find the bottlenecks. Tune Azure Functions scaling rules, configure API management caching, set up blue-green deployment pipelines, write runbooks for common failure scenarios, document the architecture for operations teams, and train your support staff on how to diagnose agent connectivity issues. This is the operations phase, and it's where many projects fall apart because developers love building, they don't love documenting, they don't love writing runbooks, they don't love load testing, but operations teams need these artifacts. When an MCP server fails at 2 in the morning, the on-call engineer needs a runbook. They need to know how to check if the server is running. They need to know how to check if Entra is issuing tokens. They need to know how to fail over to the green environment if the blue environment is unhealthy. Without these artifacts, your beautiful architecture becomes a black box that breaks unpredictably. Write the runbooks, document the architecture, and test the failure scenarios before they happen in production. Specifically, you need 4 operational artifacts before launch. The first is a health check dashboard. This dashboard shows the status of every MCP server. Green means healthy, yellow means degraded, red means down. It shows request rates, error rates, and latency percentiles. It shows Entra token acquisition success rates, and it shows API management rate limit utilization. The on-call engineer glances at this dashboard and knows immediately whether the problem is in the MCP layer, the auth layer, or the network layer. The second is an incident response runbook. This document lists the common failure modes and the exact steps to diagnose and resolve them. What to do when an MCP server returns 500 errors. What to do when Entra token validation fails. What to do when Copilot Studio can't discover tools. What to do when response latency spikes. Each scenario has a diagnosis flowchart and resolution steps. The third is a deployment checklist. This document lists every step required to deploy a new MCP server version. Build the code. Run unit tests, run integration tests, deploy to staging, run smoke tests, switch the blue-green routing, monitor for errors, and roll back if error rates exceed the threshold. No deployment happens without this checklist, and no deployment happens outside the maintenance window unless it's an emergency. The fourth is a capacity plan. This document estimates request volumes, server capacity, and scaling triggers. It says how many requests per second each MCP server handles at peak. It says how many Azure Function instances are provisioned. It says what the scale-out trigger is, and it says what the maximum capacity is before the architecture needs redesign. These 4 artifacts transform your project from a development experiment into enterprise infrastructure. Now, let's talk about common pitfalls and how to avoid them at each stage. In weeks 1 and 2, the most common pitfall is building a toy example that doesn't connect to real data. A tool that returns hard-coded JSON proves nothing. Build against a real database, a real SharePoint list, or a real API. Even if the tool is simple, the connection to real data validates the pattern. In weeks 3 and 4, the most common pitfall is skipping authentication. It's tempting to test without auth because it's faster. But auth configuration is the hardest part of remote deployment. If you defer it, you'll be scrambling to add it later while the rest of the architecture is built around an insecure pattern. In weeks 5 and 6, the most common pitfall is expecting Copilot Studio to magically understand your tools. It won't. Tool discovery is mechanical. The agent reads the description and the schema. If your description says handle stuff, the agent won't know when to invoke it. Write tool descriptions as if you're explaining the tool to a new employee. Be specific, be explicit, and test with real queries. In weeks 7 and 8, the most common pitfall is exposing too much organizational context. WorkIQ has access to a lot of data. Not all of it should be available to all agents. Define scope boundaries, use conditional access to restrict which agents can query which WorkIQ tools, and review the data classification of documents before agents start reading them at scale. In weeks 9 and 10, the most common pitfall is treating agent identity as an afterthought. Your agents aren't users. They don't have managers. They don't have job titles. They have capabilities and permissions. Design the identity model from the start. Map each agent to a specific business function and assign permissions based on that function rather than copying a human user's role. In weeks 11 and 12, the most common pitfall is declaring victory after the first successful deployment. Production isn't a destination. It's a state that requires continuous monitoring, continuous tuning, and continuous improvement. Set up dashboards, define SLAs, create alert rules, and review the metrics weekly. One more pitfall spans all 12 weeks. It's the assumption that MCP is just a technical protocol, that you can hand it to the integration team and forget about it. MCP isn't just a protocol, it's an architectural pattern. It changes how your agents connect to systems. It changes how your systems expose capabilities. It changes how your security team thinks about identity. And it changes how your business teams think about what AI can do. Treat it as architecture, not as integration. Involve your security team in week 1. Involve your operations team in week 3. Involve your business stakeholders in week 5. And involve your executive sponsor throughout, because the connectivity layer you're building will outlast your current AI strategy. It will outlast your current Copilot licenses, and it will become the foundation for every AI initiative your organization runs for the next decade. That's the roadmap. 90 days from a single local tool to a production-ready connectivity layer. It's aggressive, but it's achievable if you follow the sequence. And it's the difference between running AI pilots that hit walls and running AI agents that transform how your organization works. That's the connectivity layer your agents have been missing. MCP isn't an integration afterthought. It's the structural foundation of your agentic architecture. If this changed how you think about building AI in Microsoft environments, follow me, Mirko Peters, on LinkedIn and share this with your architecture team. Because the organizations that build this layer now will define what their agents can do for the next decade.